In this video, I want you to get a sense for what the physics meaning of work and of energy are, and start to be able to make some calculations involving each of these quantities. Now, work is an especially tricky term because it's something that we use outside of physics, and it doesn't really mean the same thing. So with work, you might think of of doing your job, the thing you're paid to do. That's going to work. If you are lifting something heavy, you might say, "Oh man, that's really hard work." And in the physics sense, that may or may not be a situation where you're doing a lot of work. So in physics, we do work on an object, or a force does work on an object if that force is acted on some object that's moving in a direction that's parallel to the direction that the force is being applied. So if I go out into the parking lot and find that somebody is stalled in their car and they need some help getting off to the side of the road, and I do a really nice thing for them and offer to help push them off to the side of the road, I push that car in some direction. So say we have a car here, and I apply a force in this direction, and then the car moves in this direction as well. We have some distance or displacement in that direction. I've done work on the car. Now, if I go out and see some cars driving by on the street outside of school, and say if we look at them from the top down, we have a car that's moving to the north here, so that's our distance, or that's our velocity vector. And I run out and get alongside the car, run alongside it at 35 miles per hour because I'm really fast like that, and start applying a force in this direction to the car. We get a sense that that's a little different situation. I'm not having any impact at all on the motion of the car in the north-south direction, and I'm not going to push the car off to the west here. It's going to have plenty of friction, and I'm going to make a fool of myself here. So I'm not doing the work in this situation on the car, but I am doing work on this situation in the car. So work is a little more careful definition than in physics than you might be used to. Now, the other thing we have to pay attention to with work is that we have to have both a force being applied and a distance over which it's acting. So if I walk up to a wall and start to push really hard on the wall, and really exert myself, and I'm pushing and pushing really hard, pushing, and I'm working up a sweat, and I'm grunting and groaning and pushing on that wall. I might finish up and be panting and think, "Gosh, that was really tough. That was a lot of work." But in the physics definition, even though I applied a really big force, since the wall doesn't move, there's no displacement here, there's a displacement of 0, I haven't done any work on that wall. So this quantity of work is going to be equal to the force applied times the distance, but we need to specify that it's the force in the same direction. Force applied times displacement is a better way to think of that. We need to specify, though, that it's the force in the direction of the displacement. So you might write that as force parallel. It's parallel to the direction of motion here. Now the units on work, well, the units for force are in newtons, and the units for displacement are in meters. So one unit that we could use is just Newton meters. You might also recall that Newton was actually an abbreviated unit, an abbreviation for kilogram meters per second. So if we do kilogram meters per second times meters, the units there are kilogram meters squared per second squared. And I think I misspoke there. Newtons are kilogram meters per second squared, not kilogram meters per second. I forgot the squared on the seconds here. So that's a unit that we use for work as well. That's the base unit without any of these abbreviated units in there. Or if we want to abbreviate this thing more completely, we have another scientist who did a great deal of work in the field of energy and how energy and work are tied together, a man named James Prescott Joule. And so the other unit would be a capital J, which stands for Joule, spelled like this, and named after James Prescott Joule, not Joule like a diamond or a gemstone. So any of these is an acceptable unit for for work. So we need to keep in mind here that we've got newtons and meters in here. So if our displacement is in, say, centimeters or miles or inches, we need to do a conversion before we can get our answer in joules or newton meters or kilogram meters per second squared. Likewise, if we had a force that weren't given in newtons, say it were given in pounds instead, we'd need to make some conversion there, or at least acknowledge that our final answer units are not going to be these units. They would be something different. So if you push something with a force in pounds and it moves a certain distance in feet, we do a certain number of foot-pounds of work on that object. That'd be one unit we use in the English system, or the imperial system, rather. Okay, so what about this situation where we have motion to the right? We've got 15-meter displacement to the right for this object. So maybe it's being dragged along the ground here by this force that's up at an angle. So maybe I have some big heavy thing that I'm pulling along with a rope, and it's not as heavy as, not as tall as I am, so that rope kind of is going up at an angle to where I'm holding it. But anyway, we're applying a force that's not quite in the direction of displacement. Well, we need to figure out what the part of that force that's parallel to our displacement is. We want the parallel component of the force. So this displacement is in the x direction. That means I need to know the x direction component of this force. So this would be F parallel. Okay, so if I want to get the work done, then I need to first find F parallel, which is going to be the hypotenuse of this triangle, 250 newtons, times the cosine of 35 degrees to get the x side of this. And so typing that into my calculator now, 250 times the cosine of 35 degrees gives us 204.8 newtons. And then work is equal to F parallel times the displacement, the magnitude of this displacement. So that'd be 204.8 newtons times 15 meters. So multiply that answer by 15 meters, and I get 3,071.8 joules, or looking at sig figs here, all these numbers have 2 sig figs, so my final answer on this work is going to be equal to 3,100 joules. Alright, now what if my force, instead of being applied up in this direction, what if it were being applied back this direction? So if we still had the same angle here, 35 degrees, and the same force is 250 newtons, what then? It seems here that I'm kind of acting against the motion of this thing, and we need to reflect that in our calculations as well. We would do that by just noting that the F parallel and the displacement vectors, those are in opposite directions. So I'd use a positive number for one of these and a negative for the other, and it doesn't matter which way we do that. We'll end up with a negative amount of work being done on this object. So if it were the same situation, just that 35 degrees was above the left direction instead of above the right direction, we just get a negative 3,100 joules for our answer here. Next, let's talk a little about energy. Now, one definition that works nicely for us for energy is the amount of work that an object is capable of doing on another object. So it's almost like energy is how we store work that we're going to do in the future. So if I want to lift something really big and heavy, I need energy in order to do that. I'm going to do work on the object when I lift it. I need energy to do it. And I get my energy by eating food. And that food has chemical energy stored in it. And this energy is stored as a result of the interaction between the atoms and molecules and how those are all arranged. We call that chemical energy. And so my body's able to release that, and I move my muscles, and we have other energy types involved there. But I have to have energy in order to do work. And the more energy I have, the more work I can do. And so energy also uses units of joules. And we use units of joules because, well, we're saying energy is how much work we can do. So if I can do 50 joules of work, that means I have 50 joules of energy. So we could do joules, we could do kilogram, meters squared per second squared again. We could do Newton meters. Any of these are equivalent. Joules and Newton meters, those just include abbreviated units. So this energy is the capability to do work as a result of either the speed of some object, how fast it's moving. So think about car crashes. One car can push another car, apply a force to it and cause it to move some distance. It can do that if the car is moving and it's colliding with the second car, say, at rest. And then the faster that first car is moving, the more force and the more distance it can cause to happen on the at-rest car. So the faster that car is moving, the more energy it has. Now this energy that's associated with motion, we call the kinetic energy. And I'm realizing there's a spelling error there, no E at the end. The kinetic energy is the energy an object has due to its state of motion. And so the equation we use for this is a capital K. Sometimes we write out KE just to distinguish this. K gets used a few different times in physics, so KE might be easier to use. Kinetic energy is equal to 1/2 times the mass of the object times its velocity squared, or times its speed squared here. So as we have larger objects, they'll have more kinetic energy at the same speed than a smaller object. And for two objects that have the same mass, the one that's moving faster will have more kinetic energy. So again, thinking back to the car situation, if we have one car that's at rest here and another car that's moving toward it with some speed v, if v is just a little tiny, then we have a fender bender. And so this car gets a little bit of a force forward, and it moves forward a little bit, a little displacement. So we do a small amount of work to this car. If this one's going really, really fast, well, then that force and displacement are going to be larger. Likewise, if we take this object and we make it not a car, but a giant truck, a semi moving this direction with a speed v, we understand that, that's going to be way worse for this car here. There's a lot more force and a lot more distance or displacement that are going to take place here. Last up, we have this relationship called the work-energy theorem, which just says that however much work is done on an object, that's exactly equal to how much that object's energy changes by. So energy is the capability to do work. When I use some of my energy to do work, the amount of work I do is exactly equal to the amount of energy that I use up doing it. The other form of this is true, or the other side of this is true. The amount of work that I do on some object is exactly equal to the amount of energy that changes, the amount of change in energy for that object. So if we think about a situation involving football, we've got a 75 kilogram football player moving at 3.8 meters per second, and we want to know how much work it's going to take to stop them. Well, initially, this football player is moving at 3.8 meters per second, and so it has kinetic energy. They have kinetic energy because they're moving. They have mass and they have speed. We want them to stop, so we want speed to go to 0, so kinetic energy is going to go to 0 as well. So in this case, we're talking about changing kinetic energies. The amount of work needs to be the change in kinetic energy. Or we can write that as kinetic energy final minus the kinetic energy initial. And so work then is equal to 1/2 mv final squared minus 1/2 mv initial squared. And continuing this down, I've got 1/2 times the mass is 75 kilograms. We want to stop this person, so we'll have their final speed be 0. Minus 1/2 times 75 kilograms times the initial speed is 3.8 meters per second. and that gets squared. So the amount of work that we need to do on this person, this whole term goes to 0, so we just have 0.5 times 75 times 3.8 squared. We get 541.5 joules, and that's a negative number. Okay, and then to answer the second part of the question, if we have our football players stopped in a distance of 1.3 meters, how much force had to be applied to them? So we know that we had to do negative 541.5 joules of work on this person. So now we can go over to the equation for work that relates force and distance. So work is equal to F parallel times the displacement d. And we know that work has to be negative 541.5 joules. And that's going to be equal to the force parallel times the 1.3 meters. And we know that force parallel and displacement are in opposite directions. It tells us opposite the direction of the motion of the player. So let's just say this 1.3 is a negative 1.3, and then the force is going to be a positive value. We could do it the other way too. So in this case, we get our parallel component of force then is equal to 541.5 divided by 1.3, or 420 joules. Or sorry, 420 newtons once we round for sig figs. And down here, since I'm done with that number, I'll go ahead and round that as well, negative 540 joules.